Hey guys, today we're going to be talking about motion, specifically position, displacement, and the differences between average and instantaneous velocity and acceleration. But before we get to all of that, we have to talk about reference frames. Reference frames are just coordinate systems with an origin and axes. But reference frames are essential to describing motion because imagine we have a particle that is located here. With respect to the first reference frame with axes x, y, and z, we can describe its position with this vector. Now guys, if you're not familiar with what a vector is, it's very simple. It's a mathematical object that can be described with magnitude, which in this case is the length of the vector, and direction, which is the orientation of the vector, or where the arrow is pointing towards. However, with respect to the other reference frame, the particle's position looks very different. If I can draw a straight line, it looks something like this. So you can see why we have to specify a reference frame in order to describe motion. And guys, when you're solving problems, usually the reference frame is going to be the Earth unless it's otherwise specified. So you can use that assumption in mind. So now we're going to be talking about displacement. Imagine we have a number line here and 0 is going to be over here and the right indicates the positive direction and the left indicates negative direction. So let's say we have an object that at time t1 is over here at position x1, and at time t2 the object has moved over to the left at position x2. Now, displacement is also a vector, so we can draw an arrow going from the initial position x1 to the final position x2. So that would look something like this. We can write displacement as delta x, which is the change in x. That delta means the change in. And that would be the final position minus the initial position. So displacement, to summarize, is defined as the change in position of an object. So what do we notice about x2? Well, x2 is negative and x1 is positive. So a negative number minus a positive number is always negative. So delta x is negative, right? Which means that it makes sense that the arrow, the vector of displacement, is pointing towards the left. And if it was pointing towards the right, that would mean displacement is positive. Or in other words, the particle has moved to the right. It can start anywhere, and as long as it moves to the right, the displacement would be positive. And as long as it moves to the left, the displacement would be negative. Now guys, an important distinction has to be made between distance and displacement. Because imagine we're going around in a circle. Pretty nice circle, right? And let's say at time t1, an object is over here near the top of the circle, and it makes its way down in this counterclockwise direction back to its original spot at time t2. So, okay, the displacement is the change in position, but the position hasn't changed at all. That means that delta x is literally 0. But that doesn't mean that the particle hasn't moved. No, it's moved a distance, which is the circumference of the circle. It's moved the entire circumference of the circle, and that is not 0, of course. So that is why distance is not equal to displacement. Okay, now let's talk about what average and instantaneous velocity are. So average velocity is represented with v with a line over it, and usually instantaneous velocity is just represented with a v. All right. Now, average velocity is defined as the final position minus the initial position over the final time minus the initial time. And you'll notice that that's literally the displacement over the total time elapsed, or the time interval that the object is moving in. And that differs from the instantaneous velocity, which takes velocity at an instant. And it's kind of like a function in that it takes a specific moment in time. Now, the definition of instantaneous velocity does require you to know what a limit and ideally what a derivative is, but it's going to look something like this. It's the limit as the time interval approaches zero of the final time, which you could just write as the position at time t plus the time interval, which is the final position, minus the initial position, which is the position at time t, over the time interval delta t. Now, you might notice that this is just the definition of a derivative, which is written as the derivative of x with respect to time, or dx dt. Okay, but the average speed is also different from the instantaneous speed. Now, average speed is actually distance, the total distance, or the total length that the object has moved in its path of motion over time elapsed. Okay, so in this circle example, if it's moved, say, 6 meters in 2 seconds, then the average speed would simply be 3 meters per second. However, the average velocity you would expect to be 0 because the displacement is 0. But instantaneous speed is a little different because it's the magnitude of velocity, or of instantaneous velocity. And you would have to really understand what instantaneous velocity is. This is so important, you guys. Instantaneous velocity takes a specific moment of time t, say, and it looks at what the velocity is in that time, right? Essentially, the limit of the average velocity as the time interval approaches 0. And then the instantaneous speed, which we abbreviate to simply speed, is the magnitude of instantaneous velocity. Okay, now we're going to move on to acceleration. So you guys already have an intuitive understanding of what acceleration is. You've been in a car before, so you can imagine that as the car accelerates, basically you are going faster and faster and faster, right? If you imagine a speedometer in your car, it's going from 0 and then to 10 and then 15, but more and more rapidly it's increasing, right? It jumps up to 30, and soon enough you're already at, say, 50 miles per hour. So that's the intuition behind acceleration. Now, average acceleration is very, very familiar. So average acceleration, a with a bar on top of it, is actually the final velocity minus the initial velocity over the time elapsed, or the time interval. And remember, guys, this is just delta t. So if you were given values for the final and initial velocity, and you could figure out what the time elapsed, delta t, was, then you can compute the average acceleration. And in a similar vein, instantaneous acceleration, which is also a vector, just like instantaneous velocity, is the limit as the time interval approaches 0 of the final velocity minus the initial velocity over the time elapsed. In other words, it's the limit of the average velocity as the time interval approaches 0. Okay, guys, just to give you a quick computational example, let's compute the average acceleration of a car which at time t1 has a speed of 3 meters per second, and at some time later, at time t2, it has a speed of 10 meters per second. Average acceleration would be 10 meters per second minus 3 meters per second over the total time elapsed, which let's say happens to be 100 seconds. The average acceleration is very slow. It's 7 over 100 meters per second squared, right? Note the distinction in the units. Velocity has the unit meters per second, while acceleration has the unit meters per second squared. Okay, guys, last thing. We're going to consider these 4 situations. Now, in the first 2 cases, the velocity is going to be pointed in the positive direction. We're going to have positive velocity because we're moving from x1 to x2, so the direction of motion is to the right, so the direction of the velocity vector is to the right. But consider what happens when we have the acceleration vector be positive as well. Well, okay, that just means that the object, let's say a car, is moving faster and faster and faster from x1 to x2. Now, what about the second scenario? What if the acceleration is pointed in the opposite direction, negative? What would happen here? I'm going to give you guys a few seconds to think about what that might look like in real life if the object had a positive velocity but negative acceleration. Well, the object would be slowing down more and more from x1 to x2. This is a case of deceleration. The object is slowing down. Now, remember, in the bottom 2 cases, we're going from x2 to x1. So let's start from x2. And that means that our velocity is going to be negative. It's going to be pointed towards the left. Now, similarly, with the first 2 cases, imagine what would happen if our acceleration vector was pointed towards the right and also to the left. Now, I'm going to give you guys a few seconds again to think about which case 3 or case 4, represents deceleration. Now, the case in which the object is slowing down, or where the object is decelerating, is going to be case 3, because the vector of velocity and the vector of acceleration are pointed in opposite directions. So while the object is going left because velocity is pointed towards the left, it's slowing down more and more and more because the acceleration vector is pointed in the other way. Now, for the last case, you would imagine that the object is speeding up more and more towards the left. And with that, guys, that's a quick review of position, displacement, velocity, and acceleration. Thank you guys for watching.